In the last video, we talked about chain rules for calculating first derivatives of multivariable functional situation. What I would like to talk about in this video is second derivatives. We could talk third derivatives and fourth derivatives as well, but they would get very complicated. So let's go back to first year, talk about what happened then, and then talk about our multivariable function. So suppose in first year, I had that u was a function of x, and x is a function of t, and suppose I wanted d squared u dt squared, the second derivative. Well, we talked earlier, last video, that du dt is equal to du dx dx dt. So suppose now we say, all right, we want to calculate the second derivative. Well, since these two things are multiplied together, we would use a product rule. We would say the derivative of the first times the second plus the first times the derivative of the second. Now this term doesn't present any problem to me at all, because that is going to say differentiate that guy, period, all right? What about this? Now remember, the chain rule is supposed to take care of the situation where you never have to substitute from here into here. So that one is fine. What about this one? That one says, take the x dt, which is derivative of this, and differentiate it again. Well, that's not a problem. So this one is not a problem. We probably would write d squared x, dt squared. I don't have any problem with that one. That is simply the derivative of this one again. But I do have a problem with this one. This says differentiate this here with respect to t. But when I look in here, that's the derivative of this. It's going to have in it x's. So I want to differentiate this thing with respect to t when it's got an x's, but that's a chain rule scenario. What I should do is differentiate that thing with respect to x, and then differentiate x with respect to t. So it should be equal to that. Not supposed to be an x, but it's a mess. So that's clear. D x. Well, what's this now saying? Differentiate du dx, which is got x in it, with respect to x. That's simply d squared u dx squared. That means differentiate this twice. Then you've got this one and this one. That's dx dt squared. And then that one was from before. So there would be our chain rule in first year for the second derivative of this scenario. All derivatives here are derivatives either of that or that, and no substitutions necessary. Let's now compare that to a multivariable situation. Suppose I give you that z is equal to u squared v squared minus 3uv. I tell you that u is equal to x squared cosine y, and I tell you that v is equal to x cubed sine y. And the objective, find di squared z, di x squared. So that's the objective. Find that. Well, in order to get the second derivative, I'm going to need the first derivative. So let's go get di z dx in preparation for the second derivative. To get that, I'm going to need a chain rule, schematic diagram. Z, function u and v. V, function of x and y, and u, function of x and y. So if we want di z dx, we take all paths from z down to x, and there are two of them. And so we would get di z, di u, di x, di z, di v, di x. Now, what I could do, but I'm not going to do it, is I could now find out, without calculating anything here, what the second derivative is and have a general formula for calculating second derivatives in this scenario. I don't want to do that. That's somewhat more complicated, but be a good exercise for it. I'm going to fill in what we've for these full part derivatives, and then take a look. So we need di z di u, which is 2u v squared minus 3v. I need di u di x, which is 2x cos y. I need di z di v, which is 2u squared v minus 3u. And I need di v di x, which is 3x squared sine y. So there's our first derivative, unsimplified. I now want to calculate the second derivative, di squared z, di x squared. And remember, this will be meaning holding y constant, if we want to put that there, for emphasis. So I want to differentiate this big mess with respect to x, holding any y's that are there constant. Well, for purpose of differentiation, we always make a schematic. So let's make a schematic. At the top of the schematic is going to be di z di x. That's the thing we're differentiating. We're differentiating this. What do we see? We see u's. We see v's. We see x's. And we see y's. All of them are present. U's, v's, x's, and y's. But we know that u is a function of x and y, and we know that v is a function of x and y. So there would be our schematic describing function of this along with that and that. And now we want to differentiate this with respect to x. So what do? We take all possible paths from here down to the x, down to the x, and down to the x. So if we do that, for the leftmost paths, we would have di squared, let's write di by di u of di z di x, multiplying, so that's that one, di u di x. That's one path. Next path, through the v, di by di v of di z di x, multiplied by di v di x. That's that path. And then we've got this one, which is di by di x of di z di x. Now the thing again to realize here is that and that are not the same thing. This is differentiating with respect to x, holding y constant. This is coming from here, so it means you're holding everything else at that same level constant, which would be the u and the v and the y. You would be differentiating that level. Right? So away we go. It says, take your di z di x and differentiate with respect to u. Take this and differentiate with respect to u. So here we go. Differentiate with respect to u. That's all constant, because and then this derivative, who are we holding constant? That's this one. We're holding that and that all constant. So differentiating this with respect to u. Well, there's the only u in this first term, so that's a constant. The derivative of this, okay, this one, times derivative of that one. Derivative of that one is 0, derivative of this one, 2v squared. 2v squared times 2x cosine of y. So that one is that one. Multiplied by del u dx, which I already did, that was this one here. So 2x cosine of y. So that's taking care of that. Next, plus. Now it says take this di z di x and differentiate with respect to v. Again, that's constant. All I have to do is differentiate this one. Differentiate that with respect to v for u v minus 3. Multiplying, whoops. So put that in brackets. And along coming 2x cosine of y. So that's that one. multiplied by div dx. We did that before. That's this one. Multiplied 3x squared sine y. So now we've got that one. Now this one says differentiate this thing with respect to x, pulling all the y's and the u's and the v's constant. So plus. Differentiating with respect to x. That's constant. 2uv squared minus 3v. Differentiating 2 cosine of y. So that's that one. And then we have differentiating now this with respect to x. So that's a plus sign. There's the only x's, so we'll have plus 2u squared v minus 3u multiplying with respect to x, 6x sine y. And there it would be. So there's how we handle a second derivative. We need a schematic for the first derivative. We look at the result, and we make a schematic from that, and we do this appropriate chain rule. You can imagine how complicated it would be if I now said I want the third derivative. I would need a schematic for all of this. It would look exactly like that, but all the derivatives in that chain rule would be much more complicated. So there's an example then of second derivatives via chain rules. What I'd now like to do is one of the exercises. This is exercise number 27. I see problems like this quite often on midterms and final exams, so I think it would be a good idea that we did one like it. Here's what it says. It says, if f of x is differentiable, so that's a function that's got a derivative. It says, show that a function of x and y equal to f of 4x minus 3y plus 5y minus x satisfies the following equation. 3 du dx plus 4 du dy is equal to 5. Okay? So it says you're going to have to calculate du dx. You're going to have to calculate du dy, multiply 1 by 3, the other by 4, and get 5. So first thing then is to differentiate this with respect to x. I have no problem differentiating this with respect to x. But what about this? Now let's clearly understand first of all what this means. What this means is that you are given this function of s, and somebody might not say that to you, right? And it says whatever that function was, every time you saw an s in it, you dropped in instead 4x minus 3y. For instance, suppose f of s is equal to the logarithm of s plus 1 over s squared. That would mean then that f of 4x minus 3y would be the logarithm of 4x minus 3y plus 1 over 4x minus 3y squared. That's what that notation is supposed to mean to us. That you simply take all the s's and you replace them by this. I would suggest that what we do is that we rewrite u in this way. That is f of s plus 5 y minus x along with that s is equal to 4x minus 3y. And the objective is to calculate du dx. Well, to me, this is a multivariable chain rule situation. You got u depending upon s and y and s depends upon x and y. So we should make a schematic. U at the top, that's what we're going to differentiate. What's the function of? S and y and x. But s is a function of x and y. So in order to calculate du dx, we'll take the two paths, one through s and one straight to the x's, and make up our chain rule. All right, here we go. So for the first path, we would have di u di s x. And for the other one, we would simply have di u di x. Notice again, this is not the same as that. This one is coming from here, so it really means hold s and y constant. Right? So di u di s. Di u di s says, go take u as a function of s, right? U is a function of s and x and y, and differentiate with respect to s. So take this and differentiate with respect to s. Holding, therefore, came from here, the y and the x constant, which means hold that one constant, and differentiate this with respect to s. Could I write then f prime of s for that di u di x? Then di s di x. That means differentiate this, 4, plus this one. Differentiate this with respect to x, holding the s is constant, holding the y is constant. How about then minus 5? How does that look? Similarly, di u di y is equal to taking the two paths down to the y's. Di u di s di y plus di u di y. For the two paths, that one and that one. Di u di s, that's f prime s again. Di s di y, differentiate respect to y, minus 3, plus di u di y, holding, that was this one, holding s and x. So differentiate this with respect to y, holding s is constant, so you're gone, holding the x is constant, so you're gone, plus 5. Plus 5. And we're now supposed to do that combination on the left of taking 3 times the x derivative plus 4 times the y derivative and see what happens. So 3 di u di x plus 4 di u di y is equal to 3. Di u di x is this, 4 f prime s minus 5 plus 4 times di u di y minus 3 f prime s plus 5. And notice, that and that are the same but opposite signs. So that one cancels that. Then we've got minus 15 here, we've got plus 20 there. That's 5. That's what we want. All right? So I've seen again that on many exams. If somebody didn't give me this and simply said, f is a function and here's u, then you've got to say, I need to give that guy a name. Here, it was suggested. On a test, it might not be suggested. You might have to do that on your own. Let me talk about something called homogeneous functions. Homogeneous functions have a lot of interesting properties. We're only going to talk about one of them. Let me tell you what about a function. A function, f of x and y and z, is said to be positively homogeneous degree n if the following is true. If, when you take all the x's and replace them by tx, you replace all the y's by ty, and you replace all the z's by tz, if the following is true, then you call it for all t greater than 0. That's an n. If that happens, we take all the x's in here, replace them by tx, replace all the y's by ty, replace all the t's by tz. If this happens, you will call it positively homogeneous of degree n. For example, suppose f of x and y and z is equal to x squared y plus zx y is this, right? I claim that is positively homogeneous. To test, I would take each of the x's, each of the y's, and each of the z's, and replace them by that. I would look at f of tx, ty, and at tz. If I did that, I would get xt squared, yt. I would get zt, xt, and yt. The question is, does a common factor of t come out of all terms, leaving you what you started with? The answer is yes. You can factor out t cubed out of here, and you get x squared y. You factor t cubed out of here, and you get x, y, and z. So that's t cubed times what I started with this guy. So therefore, positively homogeneous of degree 3. So there's a positively homogeneous function. Certainly not all functions are positively homogeneous. Let me take a couple more and we'll ask whether they are or whether they're not. Suppose I wrote just a function of two variables, f of x and y, is equal to x plus y squared. Is that positively homogeneous? To test, you would say f of tx, ty is equal to tx plus ty and squared. Now you get a common factor of t to the same power coming out of each term, and the answer is no. This one is not equal to some power of t times this. Out of here comes a t, out of here comes a t squared, and it doesn't work. So not homogeneous. What about this one? F of x and y is equal to x squared plus y squared, e to the y over x minus xy. Is that one? So nicely, in this example, polynomial stuff, in this polynomial stuff, but now I throw in some exponentials. I could throw in triggies, and I could throw in logs, I could throw in anything. To test, you say, put in tx, put in ty. So you would get xt squared, yt squared, e to the yt divided by xt minus xt yt. And now you ask, does a common power of t factor out of every term? Out of here comes a t squared. Out of here comes a t squared. These t's cancel. Out of here comes a t squared. Looking pretty good. Factor of t squared then. You get here x squared, here y squared. We cancel e to the y divided by x. And then we get minus xy. Is this the original function? The original function was this one. The answer is yes. So this one is positively homogeneous of degree 2. So some functions are homogeneous, some are not. These homogeneous functions, if you were studying differential equations like in Math 2, there's a certain kind of differential equation that is called homogeneous, and it involves these homogeneous functions. One of the properties is forms of homogeneous function. And I said there are lots of properties. And this one is called Euler's theorem. It says, if f of x and y and z is positively homogeneous of degree n with continuous first partial derivatives. Then, if you take x di f di x plus y di f di y plus z di f di z, you will get n f of x, y, and z. And you may recall, when I did the video on partial derivatives, I did an example of exactly this, showed it, right? And said, I'll show you later that I didn't have to do all those calculations. I would have a result that would tell me it without doing any calculations. So look back at that one and compare this. So proof. Well, since it's homogeneous, then I can write that f of tx, ty, tz is equal to tvn, f of x and y and z. Saying that it's positive homogeneous, n says this must be true. So from this, I've got to get this. The question is, how? Well, you need di f di x. So that's suggesting then that we differentiate this with respect to x. You need di f di y, different respect to y. You need di f di z, different respect to z. So I think we need to differentiate this line with respect to x, and with respect to y, and with respect to z, and see what we get. So if you want to, I've got no problem differentiating this with respect to x. It's just di f di x, di f di y, and di f di z. It's this one. If I want to differentiate this with respect to x, I think what I need is an extra variable, like in the last example, and set up a chain rule for it. So let's say, let v be equal to tx, w be equal to ty, and u, let's keep it ordered, so u is that one, v is this one, and w is equal to tz. So let's introduce those variables. Then if we look at the left-hand side, you've got f at the top. It's a function of u and v and w. And u is a function of t and x. V is a function of t and x. And w is a function of t and x. And we want to calculate then di f di x for this. So let's look at that. Di f di x is equal to, we would take all possible paths down. So what do we get? Di f di u, di u di x, di f di v, di v di x, di f di w, di w di x. So that's our chain rule from the schematic. All right. What can we calculate? Well, we can't calculate this because I didn't tell you what f is, so that has to stay. But di u di x differentiate this with respect to x, t. So we will be able to say t di f di u. Next one, again, that I don't know, this I do know. Di v di x, di v di x, di v di x, di v di x. no x's. All right. Die w die, and then we need, okay, so that one appears to be gone. Then we need the next one. Die f, die w, die w, die x. Die w, die x, there aren't any x's there, so that one's gone, and that's what we get. All right. Die f, die y equals. Schematic says die f, die u, die u, die y. Die f, die v, die v, die y. Die f, die w, die w, die y. Equal. Die u, die y. Die u, die y, die u, die y, die u, die y. There aren't any. So you're gone. Die v, die y. Oh yeah, that's a t. So it will have t, die f, die v. And then die w, die y. No y's. So simply that one. Die f, die z. You think you can write down what it is based upon what you've seen so far with the first two? I think we would hazard a guess. That would be t, die f, die w. All right. So those are these three partial derivatives. Let's now say if we differentiate this, okay, if we form that, right? Okay, what do we get then? X, die f, die x. X, die f, die x. Y, die f, die y. Z, die f, die z. Right? What's it equal to? Equal to x, die f, die x, t, die f, die u. Y times this one. Y, t, die f, die y. This one plus z, t, die f, die w. Right? What's that equal to? What's that equal? Okay, so we formed that. All right. So what did we do? We took and different, all right? So we took this. What we're doing was, although I didn't quite say that, we're taking this line, all right, and we're going to differentiate this thing with respect to x, we're going to differentiate with respect to y, and we're going to differentiate with respect to z, right? So when we took, let me write that in there instead, okay? So let me write in here. If we differentiate this with respect to x, we, all right, differentiate with respect to x, die f, die x is equal to, differentiate with respect to x is n, differentiate this with respect to, oh no, I don't want to differentiate this. Ah! I didn't want to do that. Erase all of them. Darn it. I want to differentiate this. This with respect to t. You can kind of see that. I'm not sure why I went off on that tangent. Because you'll notice I want this sitting here. The only way to get that from here is if I differentiate this with respect to t, then down will come the n that looks like that guy. All right, so differentiating this thing with respect to t. So differentiate this with respect to t. We will have die by die t of f of x. Let's put in the u and the v and the w is equal to, bring down the t, lower by 1, f of x and y and z. So I get that. Now to do this, that's this situation here, right? Chain rule. So now let's do the chain rule for this derivative. It will say die f die u, die u die t, die u die t, plus die f die v, die v die t, plus di f di w di w di t is equal to n t to the n minus 1, f of x and y and z. So I get that. And how much is di u di t? Di u di t, x. What is di v di t? Di v di t, y. Di w di t, z. So now it's beginning to look like Euler says, but what? It says you've got not x, y, and z derivatives, you've got v, and w derivatives, and you still have this t here. Well, if you want that t to go away, and you want that right-hand side to turn into this, what might you do? I think I would set t equal to 1. If I set t equal to 1, then the right-hand side becomes what I want. Left-hand side, you've got the x, and you got the y, and you got the z. Di f di u. Well, if I set t equal to 1, if I set t equal to 1, then u and x are the same, so why don't I write then di f di x? And similarly, I've got here di f di v, but I put v equal to 1, so v is equal to y, so di f di y. And finally, di f di z. So there is the proof after I corrected myself. Right? There's a similar property for second derivatives and third derivatives, but this is enough for us. As I said, there was an example back in the video on partial derivatives, and if you go to the exercises, there are some examples of this in the exercises, which you did the long way, but with Euler's theorem, you could say that's obvious. I hesitate to do the following, but I'm going to at least get it started. This is example number 12.19. Probably won't finish it, but at least I'd like to explain to you along the way exactly what's going on. We saw Laplace's equation last day, di squared f di x squared, di squared f di y squared. That's Laplace's equation, Cartesian coordinates, two variables. What I would like to do is say, there are lots of problems that you might want to solve that are far better handled with polar coordinates. I guess in the book I used v's instead of s, so let me change those to v's. And so the question is, what does Laplace's equation look like in polar coordinates? Polar coordinates are r's and thetas. So you'd like to say, what would this turn into if I were to switch it over to polar coordinates? Well, you know polar coordinates and how they're related. R is equal to the square root of x squared plus y squared. And theta, do we have a formula for theta? Reflect back to 1210, what I told you in 1210. And the answer is no. A lot of you thought this is the formula. The inverse tan of y over x. Now that's not true. It's sometimes true, but not always. It is always, however, one of these three things. It is either that, or it's this, or it's that. One of those three. And what I'm going to be doing here is differentiating this thing with respect to x's and y's, right? So it really doesn't matter, right? Whether the plus or minus pi is there or not, right? So let's put a circle around that and say, not really needed. All right. So I want to switch this over to polar coordinates. So I need to talk about di v di x in order to get that one. And I'll need to talk about di v dot y in order to get this one. Let's concentrate on this one. So what we want to do is we want to say, this means find the rate of change of v with respect to x when v is a function of x and y. I'd like to know that if I took that function, put it in terms of polar coordinates, what derivatives with respect to r and theta would I take in order to get the same answer? All right? So let's make a schematic, okay? All right? And let's put r and theta at the top, under here, and then x and y here. And use this schematic to get di v di x. It would say di v di r di x plus di v di theta di x. Now remember, what I'm trying to do is say, if I were to switch from x and y's over to r's and thetas, what combination of derivatives of the v function with the r's and the theta would be equivalent to this thing? So I like that, and I like that. That's a derivative with respect to r, and that's a derivative with respect to theta. Those I like. These ones I want to get rid of. So let's talk about di r di x. Di r di x, I can get it from here. Differentiate that. Do you get x over the square root of x squared plus y squared? Differentiate with respect to x, holding y constant. Now I could put that into there, but remember again, I only want to see r's and thetas on this side. So I'm going to switch this into r's and thetas. Well, let's see. What's x equal to? The other way around, x is equal to r cos theta, and y is equal to r sine theta, right? So instead of x, I could write r cosine theta. And instead of this, I could write r, so this is cos theta. So that's that. Di theta di x is equal to, differentiate this with respect to x. Don't need that. Derivative inverse tan, 1 over 1 y squared, x squared. Differentiate with respect to x, minus y over x squared. Equal, therefore, if I flip, common denominator and flip, x squared over x squared plus y squared, and then minus y over x squared. Cancel, cancel. Y is r sine theta. Bottom, r squared. Cancel the r's. So there's di theta di x. So we could write now then, that taking the partial derivative with respect to x is equivalent to di r di x, di r di x, di r di x, this one. Cos theta di v di r plus di theta di x minus 1 over r sine theta di v di theta. So doing these operations, when the function expressed in r and theta is equivalent to this if you're in x's. So there's our start. Now we need to talk about di squared v di x squared. We want this one. So, let's see. We want to differentiate this with respect to x, which means to differentiate this with respect to x. Are there x's there? Yes. You don't see them, but all the thetas and the r's depend upon x's. So let's write up in here, di v di x is a function of r and theta, and each of those is a function of x and y, just like we did in the last video for second derivatives. So di squared v di x squared is going to be passed down to x, that one. Di by di r of di v di x multiplied by di r di x plus di by di theta di v di x multiplied by di theta di x. This we just calculated over there. This we just calculated over there. This we have to calculate. It says, take this thing and differentiate with respect to r, holding theta constant. So differentiate this with respect to r, cos theta di squared v di r squared. Differentiate with respect to r, 1 over r squared sine theta di v di theta. Right? There's that one. Right? Differentiated it with respect to r. Right? Oh, we're not done yet. There are r's in here. So we better include those. Minus 1 upon r sine theta di squared v di r di theta. So that's that one. Multiplied by this one. That one was what we had before. Di r di x, di r di x, di r di x, di r di... It's cos theta. Cos theta. So that's that one. All right? That's this one. Now this one. Differentiate this thing with respect to theta plus, with respect to theta, minus sine theta di v di r. That's that one times derivative of this one, plus this one, cos theta, the derivative of this one with respect to theta. That's that one. Now differentiating this with respect to theta, minus 1 over r cosine theta di v di theta. Then this differentiating this one, minus 1 upon r sine theta di squared v di theta squared. And that's going to be multiplied by di v di theta, which was this one, di v di theta, no, not di v di theta di x, which was this one, minus 1 upon r sine theta. So there's that one, which you would simplify. Then you have to go do the same thing for this one and simplify. And then you're going to add them together. And if you do, tremendous number of simplification takes place. So let's put here, repeat, or say simplify and repeat for di squared v di y squared. When you substitute these into there, you get di squared v di r squared, 1 upon r di v di r, 1 upon r squared di squared v di theta squared is equal to 0. There's Laplace's equation in polar words. Laplace's equation in polar words. So there's still a fair amount of work to do. I just kind of got the ideas started by leading you to this one. Again, you have to simplify this, do the same thing for this, add them together and simplify, and it does simplify a lot. If you would like a real challenge later on in the course, we will be introducing spherical coordinates. If you think that you're an A+ student, try and find out Laplace's equation in spherical coordinates, in space. So you have this, and you switch that into spherical coordinates. It is a tremendously difficult exercise designed for A+ students, and I welcome you to try it on. Next day, we'll talk about another topic we talked about first year, namely implicit differentiation.